Hello, everyone. Thank you for coming to our talk. Actually, this is quite a nice coincidence because we are by accident building on the talk from the previous speaker. My name is Christoph, this is Thomas, and today we want to show you a couple of ways how you can do serverless computing in R. So to give you a quick outline about our talk, in the beginning we want to show you the problem that motivated our solution architecture. Then we want to go on and show you what serverless actually means, demystify the buzzword a little bit. And in the last part, we want to show you a different architecture. It's sort of similar to what you saw before, but it's maybe a bit more slimmed down. It's suitable if you don't have a very large workload to support. So I think most of you probably know this issue. You want to code your models and you want to deploy them into production. Sometimes you want to also scale it well. It should be easy to maintain and it should be cheap. So we want, in a sense, what we want to have is this. And when you talk to corporate IT, most of the time they are like, yeah, probably not. So
now that we've shown you the animal we like, we also want to show you a high-level view of the architecture that we like. It's quite similar to the one that Angus just presented. Let's go through it. On the very left, you see the data source, and we usually have a split between training and scoring. So the first step would be we get the data from the data source, start some kind of batch process using Docker technology, and just train models. The trained models are stored in some kind of storage, maybe a blob storage in a serialized way. And at some point of time, after a certain time or a certain event, a trigger is being activated at the top left corner, and auto-scaling and scoring is being triggered. This means the latest scoring data is being loaded from the database, the stored trained models are being loaded, and the data is scored against the models, and the results, the thing we're interested in, is either stored back into the database or sent somewhere via REST. But maybe let's step a short step back and talk about what serverless actually is. We found a neat definition on serverless.com, and just like serverless internet has wires somewhere, serverless architecture still have servers somewhere. What serverless really means is that as a developer, you don't have to think about those servers. You can just focus on your code. And this is actually the promise of serverless. What are the main advantages? First of all, there's much less administration. You don't have to provision servers. You don't have to maintain them. You don't have to worry about hardware or operating systems. Everything in that regard is being abstracted away. The second advantage, scaling on demand. Scaling is usually a huge part or at the very core of the service being provided, which means it is usually done completely automatic. As scaling is being done automatically, billing is also tied to the resources that you're using. So if you're not using any resources, you usually don't have to pay. And lastly, a faster turnaround. If you want to spin up a new environment for experiments or to test something, this is usually done much quicker. If we take a look at the historic evolution of the cloud, you can see on the left side the typical tech stack. Usually a company was responsible for handling everything. It starts with the hardware, setting up a network, patching operating systems, security, scaling, and finally writing the applications that you actually want. But over time, service providers started to take over more and more layers of this stack. So infrastructure as a service, which are usually virtual machines, means that many parts of the lower layers are being handled by the service provider. So up to the virtualization layer, you don't have to worry about anything. If you take this one step further and arrive at platform as a service, you don't even have to worry about the operating system anymore. This is usually Docker or container technology. And if you even take it one step further, you arrive at functions as a service, which means you don't even have to worry about security or scalability. All you have to focus on is your own code. And all three of these later technologies can be considered as serverless. We're going to have a very quick look at the cost. You always hear about serverless being incredibly cheap, and it is. If you just have one function call, it costs next to nothing. But if you call them by the hundredth of the thousands, and if you have runtimes not in microseconds but in seconds, and if you allocate a lot of memory, this can get expensive. So it's not always cheaper, and especially in functions as a service, there is quite a big lock-in potential on a downside. Good.
Yeah, as we have seen in the previous talk, there's basically two different scenarios that you can do serverless computing that have different requirements. The first one is training, which usually consists of long-running tasks that are resource-intensive. You might want to use GPUs for that, for example, and it's usually done in batch mode. The second one, scoring, mostly just short-running tasks that are computationally not very expensive, and they are either in an ad hoc or in a scheduled fashion. The second part is what we are focusing on today. When we looked at different options at deploying serverless scoring models in our company, we started with AWS Lambda, then went to the pendant in Azure, which is Azure Functions, and we ended up implementing a solution based on Azure Container Instances. And Thomas will briefly give you an overview afterwards. So in a sense, what we wanted to do, we wanted to be able to support different triggers. At the minimum, we wanted to be able to respond to HTTP requests and to have a function run on a schedule. Deployment of a custom runtime should also be supported. Some of our data scientists used to work in Python and some in R, so it was a huge requirement that both runtimes should work equally well. It should be possible to easily load model objects and at the end also serve them in an easy way.
Okay, so the first option we looked at is called AWS Lambda. It's the functions as a service by Amazon, and R is not being one of the few supported languages. However, Amazon gives you the possibility to upload your own custom runtime, and this is exactly what we did. So on the left, you will see something that we call a base layer. It's nothing but a zip file, including an entire R installation. So with AWS Lambda, you're allowed to upload up to 5 different layers or 5 different zip files. In our case, we have to get the runtime up there, which means we package it in the base layer, upload it, and then we have 4 layers left to upload any dependencies our R code might have and the R code we wrote ourselves. You can use Packret to manage packages. It works. If you want more information, there's a great Medium post by Philipp Schirmer who explains it a bit more in detail. However, there are a few disadvantages to it. So you can only use 5 layers, and the extracted file size of all those zip files is limited to 250 megabyte. This is not as much as it might sound at the beginning. But also, if you're using compiled packages, it gets tricky. It's doable, but it's not easy. And if we take a look at the function as a service by Microsoft called Azure Functions, you see on the left side the architecture of Azure Function version 2 right now, which means you have at the bottom the host process runs entirely on the .NET core framework and connects to different supported languages, for example, C# or Java or JavaScript, R again not being one of them, using 2 different technologies. The first one being the gRPC framework, the Google Remote Procedure Call framework, and the second protocol buffers or protobuf, serialized data format. Our dear friend Florian Schwendinger, who's also part of the team and here today, did a lot of work there. There's also other work being done in the community. Neil Fultz is providing a gRPC package, and Dirk Edelbüttel is also providing a protobuf package. However, getting all those interfaces to work correctly, handling errors, turned out to be really difficult and troublesome. Which is why we're looking at Azure containers right now.
Yeah, so as Thomas already said, while it's possible to run R in a function as a service environment, there are a few problems. If you want to support arbitrary runtimes, it's doable, but it requires quite some upfront work. And while it's also possible to support compiled libraries, it's kind of a headache, especially if you need to work around the file size constraints. For example, with AWS, what you need to do is you need to compile all your libraries against the AWS Lambda Linux image that's used in the background. Especially if you're working in corporate settings, you might not be able to convince IT to help you do that. At least that's our experience. If you use containers, as the previous talk highlighted, you have no problems with compiled libraries. All of the triggers that are supported by function as a service, we can support with logic apps. We will show you in a minute. You also have a very low vendor lock-in because if you decide to move to a different provider, as long as they support Docker containers, you're good to go. And you can also pay as you go if you want to. Obviously, the main drawback of this setup is function as a service relieves you of the maintenance of the container file. So you have to still maintain a Docker image. It's not that much of a burden in our opinion, but still. And you have a higher startup time compared to a function as a service depending on the image that you use. So briefly, our architecture looks like this. At the very top, you have a logic app, which is more or less used to orchestrate different services in the Azure cloud. You can have a different service for AWS, and there's a similar one in Google Cloud. But since our company is on .NET, this is the stack we use. The logic app can respond to different triggers, let it be an email, time, schedule, whatever you want, or for example, a file uploaded to a blob storage. The logic app then triggers spawning of a container instance. This can be a 1 to n Docker containers, where you can specify the amount of compute and working memory you want to use. This container instance then pulls a Docker image of your choice, usually from your private Docker repository to the instance, does the scoring, and in the end it serves the model output either as a REST with a RESTful interface, or it writes it to some database or a blob store. Logic apps are actually pretty cool in my opinion because they offer you, you can either code them, but you can do quick prototyping with a graphical user interface, which is quite nice, especially if you want to talk to business people because they can quickly understand how your app is going to be triggered. So on the left, you see how a very easy workflow can look like. At the beginning, we have an HTTP request that triggers the creation of a container group. In the until part, we check if the container group is successfully spawned and if everything is running properly. And in the end, when the whole setup exits, hopefully successfully, then we delete the container group so we don't incur any costs anymore. On the right, you see the underlying code that gets generated by the graphical user interface. So what it is, in a sense, is just a huge JSON file, which makes it very convenient to version control and to modify in a programmatic fashion. So that's what we do in a sense. To give you a high-level overview, how you can set up a scoring architecture. As I already said, at the beginning, you can specify the type of trigger you're looking for. Then you have to create your container group and specify the different requirements for compute. And in the until part, you have to check if the container group creation process actually is successful. Most of the time, this shouldn't be an issue, but it might happen that due to some networking stuff, or like there could be a problem in the region you're spawning your instance, that it might time out, for example. So what we are doing here is we are giving Azure a couple of retries in order to set everything up properly. And the moment the container group runs and the script is executed, we check the left condition is true and the containers get deleted. So our idea is to build a package called Serveless that helps you to automate the setup. What we already did is we built a prototype that's already working with kind of a lot of duct tape at the moment. And what we want is to build a fully fleshed out package that we can contribute to CRAN and maybe also provide an RStudio add-in so that you can easily modify stuff like number of CPUs and working memory that you want. I want to quickly give thanks to Hong Oi from Microsoft. He did awesome work for like Azure computing with R and also for AWS and Google. There's lots of packages in the Cloudy R repository if you want to interface R with different cloud providers. So do check it out. I think it's really great work. Any questions? If not, feel free to reach out to us if you have.